So today I will tell you about somehow an extension of Dempster-Shafer theory, which I call the epistemic random fuzzy set theory. And I will show some application. I will show you some application to machine learning. Okay, so this is so modeling uncertainty, as you know, is a fundamental problem. I know every one of you knows it already because you are here. In artificial intelligence or computational intelligence, we're interested in modeling uncertainty for reasoning with uncertain knowledge, making decisions under uncertainty, and quantifying prediction uncertainty in machine learning. And this last topic has become very popular nowadays. As you also know, because now it's a third day, I think, or even fourth day. So probability theory is actually too limited. So there has been a number of alternative models for representing uncertainty. And two of these models, maybe the main two models, are Dempster-Shafer theory on the one hand and possibility theory on the other hand. So Dempster-Shafer theory, as you all know now, is based mainly on two main ideas. One is to represent items of evidence by belief functions, and the second one is to combine them by this operation that we have seen now many times, Dempster's rule of combination. Possibility theory is based on the representation actually of, we can say, flexible constraints on unknown variables by possibility distributions, okay, which gives us possibility measures. And typically possibility measures are combined by some kind of operator with some properties called triangular norms. And actually, as we will see, Dempster-Shafer theory is somehow based on random sets. Okay, I showed that in my first talk, and also in Professor Chunai, also he showed us this kind of he called it a Dempster model, I think. So it's basically a random set, whereas possibility theory is based on fuzzy sets. So actually, each of these two models can be more suitable or more practical than the other, depending on the available information. For instance, if you have information that is inherently vague or fuzzy, so possibility theory is very useful. If you have uncertainty, some probabilistic uncertainty also involved, then you cannot have only possibility theory, but Dempster-Shafer theory can be used. So in this lecture, I will introduce a more general model, which is based on epistemic random fuzzy sets. And this, as we will see, this new framework unifies the two previous approaches and therefore gives more flexibility in applications. Okay, so this is a general picture. So at the bottom, you have the early formalisms. You have probability theory on the one hand, which is based on, like, say, pure randomness. Okay, you just assign probability. If you have a finite set, you just assign probability masses to points, okay, or to elements of that set. On the other hand, you have what I call Boolean possibility theory. It's based only on sets. It's a kind of thing that you have if you have only set-based information. For example, you have some unknown information. You just know it belongs to some set. Okay. For instance, interval analysis is based on this. You have some unknown quantities, and the knowledge is just that each quantity belongs to some intervals, for example, or to some set. Okay. And then you can just say whether it is possible, yes or no, that the random quantity has some value. Okay. And so this is a Boolean possibility theory. Then at the next level, the second generation, I would say, of models, you have Dempster-Shafer theory on the one hand, which is based on random sets. So it extends both the set-based approach and the probabilistic approach. And on the other hand, you have possibility theory, which is based on an extension of the notion of set, which is fuzzy sets. And then now what I will talk about today is this further generalization of possibility theory and Dempster-Shafer theory. So I will first recall the first two frameworks, okay? So you have now heard a lot already about Dempster-Shafer theory, but I will introduce it in a more general way, okay? In particular, I will not assume in this talk that the frame, what we call the frame of discernment, the universe's discourse, is finite. Okay, so I will give a more general presentation. And then I will briefly remind some definitions and properties about fuzzy sets and possibility theory. Then I will introduce the new thing, random fuzzy sets. And then I will also, so I will give first general definitions, and then I will introduce some practical models, okay? Because if you have a very nice mathematical theory, but nobody knows how to use it in applications, okay, it's interesting for mathematicians, but here we not pure mathematicians, okay? So we want to apply this model to some practical applications. So I will describe such practical models, and then I will, in the third part of my talk, I will show an application to machine learning. Okay, I will show you a specific neural network model, which is based on this random fuzzy set, and it's a model that gives, as a prediction, a belief function, okay, but for regression problem. Okay, so a belief function on the set of real numbers, not a belief function on a finite set, as we have seen in classification or clustering. Okay, so this is a definition of a random set, okay, and we have seen this kind of picture already, and this is how I introduce the belief functions, and Professor Chunlai also has shown this kind of picture. So typically we have here a probability space, okay, a space on which there is a probability measure defined. So sigma sub omega is a sigma algebra that allows us to define a probability measure. And we have here this set, okay, which is a measurable space. It means it is a set theta, and it has also a set of events, okay, which is defined. Okay, if theta is finite, the set of events is just a power set. Okay, but for an infinite set, we may have to need some subset of the power set. And then you have this mapping, here I denoted by x bar, which maps each element, small omega, okay, in capital omega, to a subset of theta. Okay, so remember the random code metaphor, okay, omega was some code, okay, and the image was the meaning of the message if that code was used. Okay. And so this defines a random set, but we need to have there's some measurability condition, which is that for any event in the set theta, okay, so any event B in a subset of theta, the set of omega whose image intersects B should be an event in omega. This will be important because we will need to give some probability value to this. So it must be an event. Okay. Okay. So that's just this property is called strong measurability. Okay. In general, you will not need to care about it, but it's just if you want to be rigorous, we need to impose this property. So the images here, or this mapping, are called the focal sets, okay, or the random sets. So we have seen that in Dempster-Shafer theory, a random set represents a piece of evidence about some unknown variable or uncertain variable x, taking values in theta. The set omega can be seen as a set of interpretations of the evidence. And if interpretation small omega holds, we know that x belongs to the image of omega, which is a subset of theta, and nothing more. And we have probabilities on omega, okay, which are maybe subjective probabilities about which interpretation is a true one. So for instance, here, this is an unreliable sensor example. Assume that some sensor gives us some information that x belongs to some set B of values. But the sensor may be reliable or not. So if the sensor is reliable, we trust that information. So we know that x belongs to B.
If the sensor is not reliable, then we don't know anything. So we just know that X belongs to theta. And we have we know the probability that the sensor is reliable. Okay, so this is a very simple example of a random set. We call it a random set because it's like a set was taken at random. Because here it's like this probability space defines a random experiment, and the outcome is a set. Except that here it's not the interpretation. There is no random experiment in which we take a set. Okay, this is the interpretation in Dempster-Shafer theory. Okay, and then a random set defines belief and probability functions. Okay, so here for any event B in theta, we can compute the probability that the proposition X belongs to B is supported by the evidence. So this is a property, the probability of the set of omega, here in big omega, whose image is included in B. Okay, because if X bar of omega is non-empty and included in B, so if we know that X belongs to that set, then we know that X belongs to B. Okay, so this is in support for B. And we call this a degree of belief in B. And we can also define the probability that the proposition X belongs to B is consistent with the evidence. So this is a probability here in that space of the set of omega whose image intersects B. Okay, and here these two subsets of omega are events. We can compute the probability because we have imposed this property, okay, this measurability property. It's obvious for this one, but we can show that if all these subsets are events, this is also the case for these subsets. Okay, and the plausibility of B is 1 minus the degree of belief in the complement of B. Okay, so these two mappings, we can prove that. Okay, we can prove that this mapping Bell is a belief function in the sense that we have seen, and you have seen that equation several times with these inequalities. Okay, this complete monotonicity property that defines belief function. Okay, so once again, and this is very important to keep in mind the interpretations. In Dempster-Shafer theory, Bell of B is interpreted as a degree of support for B, and plausibility of B is a degree of consistency with B, or a degree of lack of support for the complement of B. And because this comes from this, you see, the less the complement of B is supported, the higher the plausibility of B. Okay. And here there are some examples. Okay, here, for example, Bell of B is large, and Bell of the complement of B is 0. So we have some evidence for B, okay, but no evidence that supports the complement of B. So the plausibility of B is 1, okay, because there was no evidence against B. Okay, so plausibility is 1. And the plausibility of the complement of B is low because it's 1 minus Bell of B, because B is very supported. So the complement of B is not very plausible. Okay. So here we have an example of mixed evidence. Complete ignorance. Neither B nor the complement of B is supported. So both are plausible. And in the case of probabilistic evidence, then the degree of support for B plus the degree of support for the complement of B is 1. Okay, so, and this is true for any B, so Bell is a probability measure in that special case. Okay, we know already, this is just a reminder, but you can notice that here I didn't assume omega to be finite, okay? And I didn't need any notion of mass function, okay? So this is more general. So there are some interesting special cases. So you may have precise but uncertain information. So in that case, the image of any, so if for all omega, the image of omega is a singleton, okay, its cardinality is 1, then we have a Bayesian random set, okay, and Bell is a probability measure. We can have certain but imprecise information. In that case, we have only one focal set, P, okay, so the mapping is constant, is a constant mapping. This corresponds to set-valued information. We know that X belongs to some set B and nothing more, but there is no notion of of probability or doubt. And a particular case is where that set B essentially is a whole set theta. So this is a random set that represents complete ignorance. We say that it is vacuous. So now the combination of independent pieces of evidence. So this is a repetition of things you have seen already, but maybe it never hurts to have some things repeated. But once again, here we take from the start the perspective of random sets. Okay, and the advantage of this is that we don't need that notion of mass function. Okay, so it's more narrow in a way what I'm telling now. So here we have two. Okay, I show this with two. Here we have two random sets. Okay, I take the example of two sensors. So both can be reliable or not, for example. Okay, and then here we have seen that already. So if, for example, both sensors are reliable, so sensor 1 tells us that X belongs to A, sensor 2 tells us that X belongs to B, if they are reliable. So if they are both reliable, we know that X belongs to the intersection. Okay, and what is the probability that they are both reliable? It is a product of probability because we assume independence. Okay, so here we have the product space. It has 4 elements, and each of the two sensors can be reliable or not. So there are 4 possibilities. In each case, we can assign a probability with the product of the probabilities, and as a mapping is the intersection, okay, of the two mappings. Okay, this is a more complicated case where we have some conflict. So here, the two sensors tell us two things which are inconsistent. Okay, because here A intersection B is empty. So here we have to take into account here only the pairs of interpretation that don't give us an inconsistent consequence. Okay, so here we have to eliminate the case that both sensors are reliable because it gives us a contradiction. It's not possible. Okay, if our model is correct, it's impossible that both sensors are reliable. So here we have only, so we take the product measure here on the product space, and we condition it to keep on the pairs of consistent interpretations. Okay, so here there are only 3 pairs of interpretation that are consistent. Either the first sensor is reliable and the second one is not. Okay, or the second sensor is not reliable, but the first one is reliable, or no sensor is reliable. Okay, so these 3 cases do not give a contradiction. Okay, in one case we have A, in the other case we have B, in the third case we have the so-called set theta. And so practically we just assign a 0 probability to the, for example, here reliable, and we renormalize everything. So this is a conditioning. Okay. So this is Dempster's rule of combination. It is a more general setting. So we start with 2 random sets, and we define the orthogonal sum is a new random set. Okay, so here we have the product space. Here this is the set of events, okay, on this product space. Here P12 is the product measure condition of this set. Here I denote it here by theta star, the set of pairs of interpretations such whose image are disjoint. Okay, so they are not disjoint, sorry. So the set of pairs omega 1, omega 2 that are consistent. And so P12 is a product measure conditioned on this set of pairs omega 1, omega 2 that don't have empty disjoint images. Okay. And we denote this combined random set like this. So you see here, from this perspective, I put the emphasis on random sets. Okay, but basically, in that case, it's equivalent to reason with random sets or to reason with belief functions. Okay. So this rule, we have seen already that it is commutative, associative. It has any vacuous random set is a neutral element. The control function is once again the mapping that PL with a lowercase p, PL of theta is the plausibility of the singleton theta. So I have a separate notation because this is just the mapping that gives us the plausibility of any single element of theta. Okay. And we have this remarkable property that we have used many times already, that the contour function of the orthogonal sum is proportional to the product of the contour functions. And we have seen that this is very useful because many times we are happy to know only which element of theta is the most plausible. So in that case, we can just compute those contour functions and just multiply them, which is a very simple operation. And also we have this generalization of Bayesian conditioning. If X bar is a Bayesian random set, so each image is a singleton, and X sub B is a constant random set with focal set B, then the combination is actually, it gives us a probability measure, which is a conditional probability measure. And it's the same thing as Bayesian conditioning. Okay, so we have seen that already, but here once again we see it from a different perspective, from the perspective of random sets. Now, fuzzy set and possibility theory. I don't know how many of you are familiar with this. Who doesn't know anything about fuzzy sets? Don't be shy. It's normal. It's not everything. We know many things. We cannot know everything. A little. Okay. Okay. So I will just remind a few definitions. So a fuzzy subset of a set theta basically is a mapping from theta to the interval 0, 1. Okay, so you assign to each element of theta a number between 0 and 1. And this is interpreted as the degree of membership of theta to that fuzzy set. Okay. So this represents a generalized subset of theta with unsharp boundaries. Okay, and there are many examples in natural language, a set of tall people, the set of rich people. All these sets are like this. And we cannot say that an element belongs or does not belong. There is a degree of membership. Actually, almost all concepts are like this, actually. It's a simplification to consider that some proposition is completely true or false. So here's an example. Assume that theta is a range, interval minus 60, 60 is a range of outside air temperatures in degrees Celsius. So the notion of hot temperature can be represented by a fuzzy subset like this. So if its temperature is 10, it's definitely not hot. If it's 40, it's definitely hot. And in between, it's more or less hot. Okay, so this is a simple example. So some definitions here that we'll use. The height of the fuzzy set is the maximum of the membership degrees. Okay, so we say that fuzzy set is normal if this is equal to 1. And then the notion of alpha cut. If you take some number alpha between 0 and 1, the alpha cut of the fuzzy set, F tilde, it is the set of elements of theta whose degree of membership is larger than alpha. Okay? The set of elements of theta which has a degree of membership in the F tilde at least alpha. And it's an ordinary set, it's a crisp set. Okay, now the notion of the possibility theory. What is the relation of possibility theory with this fuzzy set? So here we consider X a variable taking values in theta as before, and assume we receive a piece of evidence telling us that X is F tilde. So this means that the value of X is constrained by the fuzzy set F tilde. For example, you learn that somebody has been outside and it tells you that outside it is hot. Okay, so you have some information. So now you know something about the temperature. Okay, you know it's not minus 10 degrees. You know it can definitely be 40 degrees and so on. Okay, so this is the idea of a constraint, but it's not a hard constraint. It's kind of flexible constraint. Put some constraints like value of if you know it's hot, a value of 10 degrees is definitely not possible. Okay, but a value of 25 degrees has some degree of possibility. It's possible to some extent. Okay, so this is what we try to capture with this notion of possibility theory. Okay, so we we define the possibility distribution. So it's a function that has the same value as the membership degree, okay? But the interpretation is different. For example, if you know that it's hot, and I can take this, okay, I can take this example here. You know that it's hot. What is the possibility that the temperature is 35 degrees? So it is equal to the degree of membership of 35 to the fuzzy set of hot temperatures. Okay. So in one case, you have an interpretation in terms of degree of membership. In the other case, you have an interpretation in terms of degree of possibility if you have this flexible constraint. Okay. And so the answer is like maybe 0.75, something like that. So the degree, then after that, you can, for any subset B or theta, you can define the degree of possibility of B as the supremum of the degree of possibility of theta for theta belonging to B. Okay. So for instance, here, what is the degree of possibility that the temperature is between 25 and 35? So this interval is as possible as the most possible value in it. Okay, so you take the maximum, here it's the maximum because that function is continuous. You take the maximum of the possibility inside that range, and you see it is 0.75. Okay, this is Sir Martin yesterday showed, because he talked about possibility measures, okay, or possibility theory. So here you don't compute an integral. I said there is no differential element. We just take, it's just an optimization problem because we just take the maximum. Okay. So we define so this mapping is called the possibility measure. And then we define the degree of necessity like this. The degree of necessity of a set B is 1 minus the possibility of the complement of B. Okay, so for instance, what is the degree of necessity of that interval, that the temperature is between 25 and 35? So the complement, you take the complement, it has two parts outside these intervals, okay? And in that what is the supremum, it is 1. So the degree of necessity of that interval is 0. Okay? So it's not at all necessary that if you know it's hot, it's not at all necessary that the temperature is between 25 and 35, but it is somewhat possible. The degree of possibility is 0.75. Okay. So these mappings verify these properties. For any two subsets A and B, the possibility of A union B is the maximum of the possibilities of A and B. And the degree of necessity of the intersection of A and B is the minimum of the necessity of A and the necessity of B. And I've mentioned already, and this has been mentioned several times, that the necessity measure is a belief function. It verifies that complete monotonicity property. The possibility measure is a corresponding plausibility function. And here we have to be careful because for this reason, it has sometimes been claimed that possibility theory is like a special case of Dempster-Shafer theory. Okay? But we have to be careful that this is not true actually, because the two theories have different mechanisms for combining information. Because here, if you take two possibility distributions and you combine them by Dempster's rule, it is no longer a possibility distribution because it's no longer consonant. Dempster's rule does not preserve consonant. Okay, so if you have something that a theory of these possibility measures, the combination operators cannot be Dempster's rule. Okay, it has to be something else. So assume we receive two independent pieces of information telling us that X is F. So X is constrained by the fuzzy set F tilde. And second source tells us X is constrained by the fuzzy set G tilde. For example, two people have been outside. One says it's hot. The other side says it's very hot, for example. And hot and very hot are modeled by two different fuzzy sets, okay, of the domain. So we can deduce that X is constrained by the intersection of the two fuzzy sets. Okay. but we need to define the intersection of fuzzy sets. Okay, so actually, in fuzzy set theory, intersection operators are called triangular norms. They need to verify some properties, and it's called triangular norms. The two most common choices for triangular norms are the minimum on the one hand and the product. But the intersection of two normal fuzzy sets is generally not normal. For instance, if you have a fuzzy set here, assume F tilde. Okay, this is normal. Okay, and then you have here another fuzzy set G tilde, and you take, for example, the minimum. Okay, so the intersection for the minimum is like this. You just take the minimum of these two functions, you have something like this. Okay, and this is the height. Height is not equal to 1. So even though you combine two normal fuzzy sets, the intersection is not normal. Okay? So here we do want normal fuzzy sets because, okay, the meaning of a fuzzy set which is not normal is not very clear. Okay, so we want to have only normal fuzzy sets. So what we do, we normalize, okay, by dividing. So we divide this, for example, not normal fuzzy set. We divide each value by the height, okay, and so we get something like this. Here, this intersection has been normalized, so we just divide the intersection by the height, and so we get here a new operation, the normalized intersection, and this operator is associative if and only if the triangular norm is the product. Okay, if you take the minimum, it's not associative. So we do want this associativity property. So from now on, we will take the product as an intersection operator, and we will denote it like this. So this symbol denotes the normalized product intersection of fuzzy sets, or equivalently, normalized product intersection or conjunctive combination of possibility distributions. Okay, so actually we have a graph here. Okay, here we combine hot with around 30. Okay, so this in blue we have fuzzy set that corresponds to around 30. In red we have a fuzzy set corresponding to very hot. We take the normalized intersection is a broken green line, and the normalized intersection is a green solid line. Okay.
So what are the semantics for taking product versus minimum? When would you take a product? When would you take minimum as a t-norm? Yeah.
I would say that okay, if you take the product, you have a reinforcement effect. Okay, when you and it's not idempotent. Okay, so it's more, but it's more relevant probably to it has behind a notion of independence of piece of information. This has been sometimes like in books by Dubois, they justify it like this. They say it has a reinforcement effect. It's not idempotent, so it seems to be suitable for combining independent pieces of information. But and they remark that it's associative, but I never found anywhere that it is the only solution to be associative. And we showed it recently with Krajinovic. That's it's not very difficult to show. I didn't find it. Maybe somewhere in the literature, I didn't find it anywhere. This result. Okay, now I arrive at the combination of these two things. Now we'll combine these two things, and we will get random fuzzy sets. So a random fuzzy set is defined like this. We still have a probability space here, a measurable space, and the mapping now, I denote it by x tilde, maps each small omega and big omega to a fuzzy subset of theta. Okay, so it's really a generalization of the previous framework. Okay, And we impose some condition. We impose that if we consider the mapping, if we take some alpha between 0 and 1, and we consider the mapping that maps each omega to the alpha cut of the image, okay, then we get a normal mapping from omega to the power set of theta. Okay, and so we say that the mapping x tilde is a random fuzzy set if all of these alpha cuts are random sets. We want all the alpha cuts. And so the alpha cut of the mapping is a mapping that maps alpha to the alpha cut of x tilde of omega. Okay, so this defines a mapping from omega to the theta. If whatever the value of alpha, this is a random set, then we say that x tilde is a random fuzzy set.
By random set, you mean it belongs to the sigma algebra of
Random set is that measurability property I defined before.
earlier.
Yeah. That when you take B here, the set of omega whose image intersects B should be non-empty.
Okay.
Okay. So we can use this random fuzzy set model as a model of unreliable and fuzzy evidence. So we have an example here. Assume that a witness tells us that temperature was hot on Monday, but the witness is 50% reliable. Okay, so omega has two elements: either the witness was reliable or not, and the probability that the witness is reliable is 0.5. X is a temperature on Monday in Celsius with that domain, and the image of reliable is a fuzzy set that describes the notion of hot. Okay, it can be that fuzzy set I showed you before, and the image of not reliable is theta. It means if the witness is reliable, tells the truth, then we know that the temperature is hot. And so the value of x is constrained by this corresponding fuzzy set. Okay, if the witness is not reliable, we don't know anything. So I call such fuzzy set epistemic because they represent some state of knowledge after obtaining some evidence. Okay, so here I acknowledge that this notion of random fuzzy set is mathematical notion is not new. I didn't invent it; it exists already for even a long time, but it was mainly used as a model of a mechanism for generating fuzzy data. Okay, you have a random experiment, and the result of that experiment is a fuzzy set. But here it's not a model of data, fuzzy data generating mechanism. It's a model of knowledge. It was also used as a model of imperfect knowledge of a random variable, but here it's not the case. Here there's no random variable. There's no unknown random variable. Okay, so it's other completely different interpretation. Okay, so we can now assume that interpretation omega holds. For example, we know that the witness is reliable. Okay. Then x is constrained, okay, by some possibility distribution, which is x tilde of omega, the fuzzy set x tilde of omega. So we can compute if you get any event b in theta, we can define the degree of possibility of b like this. Okay, it's a maximum possibility inside B, as we have seen before, and we can define a degree of necessity in B. Okay, in that case, we purely possibilistic because we assume that some omega here is true, so X is just constrained by this fuzzy set, which defines a possibility measure, and so we can define the degrees of possibility and necessity like this. So now we can take the expectation, okay, with respect to the probability measure on omega. So we can define the expected necessity of B. So we take just like the expectation of these necessity degrees, and we call it Bell of B. And we can define the expected possibility of B, and we call it the plausibility of B. And it can be shown that this function Bell is a belief function. It's completely monotone. Okay, and PL is a dual plausibility measure. And this was shown by Zade in a paper that has been a little bit overlooked, a 1979 paper. It was not published in a journal. I think it was a little bit obscure, but actually he had this idea already. But he proved only in a very special case, and this was proved in a more general case in this more recent paper. So a random fuzzy set, just like a random set, is a way of specifying a belief function. Okay. But the random fuzzy set model is more flexible. Okay. So here we can continue the previous example, okay, with that example of the witness here. So we have this evidence. Okay, what is the degree of belief that the temperature is, okay, what is the plausibility that the temperature is between 25 and 35? So if the witness is reliable, we can compute it from the fuzzy set, that fuzzy set hot. So it is, we get 0.75. If the witness is not reliable, it is 1. Okay, so we can just compute the expectation. We multiply 0.75 by 0.5, plus this value multiplied by 0.5. We get that degree of plausibility. Okay, and we can compute the belief by averaging, okay, this degree of necessity. So but here in both cases, whether the witness is reliable or not, the degree of necessity is 0, so the degree of belief is 0. Okay. So we have no evidence, knowing that the witness tells us that the temperature is hot. We have no evidence that directly supports this, what this is, but it is somehow compatible, not quite compatible with or consistent with that information. Okay. So now assume that we have two independent random fuzzy sets. Okay. So we have two mappings like this, x1 tilde, x2 tilde. So if both omega 1 here in capital omega 1 and omega 2 in capital omega 2, if they both hold, so a non-quantity x is constrained by x1 tilde of omega 1 and x2 tilde of omega 2. So we will once again take the intersection. It's constrained by the intersection. But we need a definition of fuzzy intersection. I already indicated that we are going to take the product, okay, because it is associative. For me, it's the main thing, but also because it goes well with this idea of independence. And we need to handle the conflict or the inconsistency between the two sources, as we did with Dempster's rule. Okay. So here for fuzzy intersection, as I mentioned before, we take the normalized product intersection operator. And now the conflict. With sets, the conflict is all or nothing, because if you have two sets, either they intersect and there's no conflict, or they don't intersect and there is full conflict. Okay. With fuzzy sets, conflict is a matter of degree. Okay. So here we can define the degree of conflict actually by considering the height of the intersection. Okay, so you see here, for example, you have one case where you have some conflict because the height of the intersection is not equal to 1. Okay, if I have something like this, one fuzzy set is like this, and the other one is like this. Here, the height of the intersection is 1. You can say there's no conflict. Okay, so it's common in fuzzy set theory to measure the conflict by 1 minus the height of the intersection. Okay. If you have a situation like this, say here the intersection is empty, the height is 0, so the conflict is total here. So I will define here the degree of consistency. It's 1 minus the degree of conflict. The degree of consistency is the height of the intersection. So this is the product. okay, and I take the supremum, which is give me the height. So the degree of consistency of these two fuzzy sets, okay, is the height of the product intersection. And this allows me to define a fuzzy set of consistent pairs of interpretation. I say that the degree of consistency between omega-1 and omega-2 is the height of the product intersection of the images of omega-1 and omega-2. Okay. So instead, in the Dempster's rule, we had either the pair omega-1, omega-2 has images intersect, is not conflicting, or the images don't intersect, is completely conflicting, and we eliminate this case, okay? Here we have a fuzzy set of pairs of consistent pairs of interpretation. So we are going to take the product measure and condition it on that fuzzy set, okay? And this is possible. There is a notion of Zadeh, always the same Zadeh, he plays a big role here. He defined the notion of a probability of a fuzzy event, okay? And we can define the this conditioning operation where we condition by a fuzzy event like this, okay? So the conditional probability of B given the fuzzy event theta star is, okay, here we condition the product measure. So it's P1 cross P2 of B intersection of B with that fuzzy set divided by the probability of the fuzzy set. And this is simply, the probability of the fuzzy set is simply the expectation of its membership function.
So what if it is 0, like you draw in the second case?
If you have, you assume that, yeah, you assume that this is not 0.
Okay.
Here I don't give all the technical, conditions. Okay, we assume that this is not 0. So we have this definition of what I call the product intersection rule to combine random fuzzy sets. So the orthogonal sum of two random fuzzy sets, x1 tilde, x2 tilde, is that random fuzzy set, where you take here, this is a product measure, here is a set of events, it's a product of the 2 sigma algebra, and the tensor product. This is a product measure condition on that fuzzy set, and this, okay, this is a notation for this new mapping, the new mapping that maps omega-1, omega-2 to the product intersection of the images. Okay, I can skip this because I'm running fast. Okay, so the properties, okay, are these ones. So this mapping is commutative, associative. It generalizes Dempster's rule, both Dempster's rule and the normalized product intersection of possibility distribution, okay? Because a special case is where the two random fuzzy sets are actually random sets, okay? In that case, we get the same thing as Dempster's rule. Another case is when, if the two random fuzzy sets are constant, it's the same thing as a possibility distribution. And in that case, we get the normalized product intersection of possibility distributions. So we still get this nice property that the contour function of the orthogonal sum is a product of the contour function. Okay, and this is a very nice property because we have seen that it can be very helpful in applications. And it generalizes conditioning of a probability measure by a fuzzy event. That is to say, if we combine x star, x bar here, we have if one of the random fuzzy is a random set, it's a Bayesian random set, and the other one is a constant random set with fuzzy focal set B tilde, then the combination is a Bayesian random set, okay, and the corresponding belief function is a probability measure conditioned on B tilde. So it's consistent with the notion of conditioning by a fuzzy event. Okay, so this is for the, let's say, theoretical framework. Now we have laid the foundation, but now how do we work with this? Okay, it seems to be very complicated model maybe for you. So how I am going am I going to apply this? So we could give a very general course on probability and also have very abstract notions, okay? But actually in practice, when you make it work, okay, to make it work, you need more simple models. And a simple, very useful model of probability distribution in probability theory is a normal or Gaussian probability distribution, okay? And it's convenient because it can be easily used in calculations. For example, the sum, if you take two normal, independent normal variables, the sum is still normal, or any linear combination is normal. If you take a multidimensional normal probability distribution, you can marginalize it or condition it. It's still normal. Okay, so this is very convenient. Until recently, we didn't have anything like this with belief functions. Okay, and that's why we see very few papers applying belief functions on infinite frames, like the real numbers, for example. The theory of belief functions in our abstract spaces existed for a long time. It's actually in Shafer's thesis, published before his book. Okay, so in his book, he doesn't mention this because he doesn't want to have complicated mathematics, but it doesn't mean that he knows already all the theory for the abstract spaces in any continuous space. Okay. But we didn't have a practical model like the equivalent of the Gaussian. Okay. And I will introduce now such a model, which I call Gaussian random fuzzy number. And we'll see that this is a random fuzzy set, okay, model that will allow us to define belief functions on the real line, okay, or on R to the P, or in the Euclidean space, okay, and it's a very convenient model, okay, and now with this, we can easily apply belief functions to problems with continuous variables. Okay. And actually, by the way, in engineering, many models, for many model parameters are reals, okay, are continuous, okay? So it was a serious limitation until now that we cannot apply Dempster-Shafer theory to problems like this. So first, I introduce the notion of a Gaussian fuzzy number. A fuzzy number is a subset of the real line, okay? And it is Gaussian if the membership is a Gaussian. Okay, so this is the degree of membership of X, okay, to a fuzzy number is defined like this. So it has a mode M and a precision parameter H. The precision is the inverse of the variance. Okay, so here we reason with the precision for a reason that will become apparent later. So here we have an example. Here we have the membership function of a Gaussian fuzzy number with mode -1 and precision 1. Okay, this is in red. And in blue, we have a Gaussian fuzzy number with the mode 1 and precision 3. You see, the blue one is more precise than the red one. Okay. Then we can combine, if we have two Gaussian fuzzy numbers, their product intersection is still a Gaussian fuzzy number. Okay. And here in green, I represent the product intersection of these two. It is still in the same family. And this is very nice, important if we want to have easy manipulation. Okay? And so the precision is the sum of the precision. You see, we just added the precision of the two, and the mode is some combination of the modes of the two of M1 and M2. Okay.
So do you allow constants to be a Gaussian fuzzy number? Just a constant?
Yeah. Constant is a case where the precision tends to infinity. Actually, you can include it in the limit. So if H is infinite,
it's like a
because in that case,
delta function.
Yeah, it becomes a delta function. Yeah.
Delta.
Actually, it's not even a delta function because it's a real function. It gives us, if H is infinite, this image is 1 if X is equal to M and 0 otherwise, if even an ordinary function. Okay, now what is a Gaussian random fuzzy number? It's a Gaussian fuzzy number whose mode is random, and is a Gaussian random variable. Okay, so I denote it like this. So n with 3 parameters. Okay, so where mu and sigma squared are the mean and the variance of the mode. Okay, so imagine that you have a Gaussian fuzzy number, but it fluctuates like this. Okay, it has some variability, so the mode becomes a Gaussian random variable with mean mu and variance sigma squared. So now we have 3 parameters: the mode, the variance, and the precision. Okay, it's a Gaussian fuzzy number. Here the mode is denoted by capital N. Capital M is a Gaussian random variable. You can say it's a doubly Gaussian variable. It has the possibility is Gaussian, and the mode is a Gaussian random variable. Okay. So if there are some interesting special case, if H is 0, okay, so if H is 0, precision is 0, so in that case, the Gaussian fuzzy number becomes R itself, okay, because in that case, okay, here you go, something like this. Okay, this becomes a degree of membership. Okay, it's 1 for all x. Okay, so in that case, doesn't matter. The parameters mu and sigma squared don't matter. Okay, anymore. Okay, so whatever mu and sigma squared, we get the vacuous random set. It induces a vacuous belief function, so it corresponds to complete ignorance if H is 0. If H is infinite, the precision is infinite, then, okay, the Gaussian possibility becomes a point, and now becomes a mode, and the mode is random. So this is equivalent to the Gaussian random variable mu sigma squared. Okay, so when the precision is infinite, you get the Gaussian random variable. And if the variance is 0, then the mode is constant. So it is a Gaussian possibility distribution.
So what if sigma squared is infinite?
Sorry?
What if sigma squared is infinite?
Sigma, when sigma tends to infinite, there's nothing. There's no sigma variance cannot be infinite.
This is the identity in Dempster's model.
Okay, yeah, maybe I should have to dig this a little bit more. What happens if you let the variance tend to infinity? What are the limits of the belief and the feasibility? Okay, this is like yeah, that would be another case of maximum uncertainty, and we will get the vacuous too.
Yes,
that would be nice. Okay, I have to think about it. Yeah. So here you see we have two. I just take 10 realizations of the mode to give an idea of the feeling of the variability. Okay, so here you have low precision. Okay, it's not very precise, but it doesn't vary too much. Here it's more precise, but it has a higher variance. Okay, it's two different kinds of uncertainty. Okay, and we can, what is that with this model? We can do some calculation. For example, we can compute the contour function at any x, and it has an expression like this. Okay. So here I represent the solid line here is the contour for the red random fuzzy set, and for the blue one. Okay. Sorry, no. This is the dash line here. The dash line, okay, is a contour function. Okay. So actually, the contour function becomes 0 everywhere if you have a probability, not a Gaussian probability distribution. Okay. So the more variability, the more the maximum value of this contour tends to 0. Okay, and you can also compute here. You don't have to read in detail this formula. It's just to tell you, this slide just tell you that we can compute for any interval x, y, we can compute the degree of belief and the degree of plausibility. You can notice that if h tends to infinity, okay, here, for example, this term, because, yeah, this term tends to 0, and we get the usual formula to compute the probability of an interval for a normal distribution, okay? And here you have the degree of possibility. So here you have minus sign, so this is less than the probability of the normal distribution, and this is larger. We get an interval, okay? Okay, in particular, we can compute what we can call a lower cumulative distribution function and an upper cumulative distribution function. The lower cumulative distribution function, or CDF, is the degree of belief that x is less than y, okay? And so the degree of belief in the interval minus infinity y, and we can compute it. And we can also, we define the upper CDF as the plausibility of those intervals minus infinity y. So you have two CDFs, actually, a lower one and upper one. I draw them for these two, the blue and the red cases. And now, what is, I think, interesting is that we can combine these Gaussian random fuzzy numbers by this product intersection rule, and we still get a Gaussian random fuzzy number. Okay. So here in green, I have represented the combination of the blue and the red Gaussian random fuzzy numbers. Okay. And so we have this kind of formula. So the precision is just the sum of the precisions. Okay. But for the mean and the variance, you have more complicated formula, which are given here. Okay, you don't need to look at this in detail, but just to say that it can be computed. Okay, but the main thing is that when you combine two Gaussian random fuzzy numbers by the product intersection rule, you still have a Gaussian random fuzzy number.
Since you allow the h to go to infinity, you have to be a little careful, because then you're in this area of generalized functions, not regular functions.
You know, I did it actually. You can let h1 and or h2 go to infinity and compute the result. Okay, by taking the limit. Okay, and it's so you can define the combination of two Gaussian, the intersection of two Gaussian random variables. Yeah.
The caution is you to use a different calculus. If the regular calculus doesn't work, so you're in the field of generalized functions.
No, because as I say, no, we don't have a generalized function. We don't have need a generalized function.
But then you're not allowed to use h1. You can say 10 to infinity, but if you say they're infinite,
yeah,
be a little careful, I think.
Yeah, but I think it's explained in the paper.
Okay.
Okay, now we can further extend this to have Gaussian random fuzzy vectors. Okay, because many times we need to represent some knowledge about the vectors, vector quantities. So here, for example, so first I introduce Gaussian fuzzy vectors. And so it's a fuzzy subset of R to the P. Oh, okay. And with a Gaussian membership function defined like this. So now X is a vector. The mode is a vector. For example, here you have in 2 dimensions, this is a mode, here it's a vector. And you have a precision matrix, a positive definite precision matrix. So here I represent contours of the member of 2 different Gaussian fuzzy vectors. And now you guess that I will now allow the mode to be a Gaussian random vector, a multidimensional Gaussian variable. Okay, and so I will get. Okay, first of all, I'm not yet there. I want to observe that we can combine 2 Gaussian fuzzy vectors by the normalized product intersection. We still get a Gaussian fuzzy vector. So here I've represented the intersection of these 2. Okay, the precision matrix is just the sum of the precision matrices. And now I define a Gaussian random fuzzy vector by allowing the mode to be to be a multidimensional normal Gaussian variable. Okay, so this is the idea that you see here. Now the mode fluctuates, and it's a Gaussian vector, Gaussian random vector. Okay, so I represent here. So yeah, and here, so the solid ellipses here are the what are they? They correspond to the precedent matrix H. Okay, and the ellipses here, broken ellipses, represent some contour of the PDF of the Gaussian probability distribution. So in one case you have a description of the imprecision, in the other case you have a description of the certainty. Yes. Okay. And here again we have that if we take two Gaussian random fuzzy vectors, we can combine them by the product intersection rule, and we still get a Gaussian random fuzzy vector. Okay, and we have some. So the precedent matrix is the sum of the precedent matrices, and we can compute this, the formula Luke carry. Probably they can be simplified. Okay, this is something that I did at the end. Probably we can simplify, but at least it can be done. Okay. Okay, now I presented this last year, and somebody in a conference, and somebody asked me, say, but he was an engineer, and he told me, but the Gaussian distribution sometimes it's not good enough because it assumes some symmetry, and so that's in application, for example, filtering. It was Jean Denœux who asked me this question. In filtering, for example, or in tracking, we use some methods which are not normal because and why here, but here we are constrained with a normal distribution. So I started to think, and indeed, okay, there are some assumptions. This is Gaussian fuzzy number that of unimodality. We assume the mode is a distribution as a unimodal and symmetry. Okay, and actually it would be nice to have more flexible parametrized models of belief functions or random fuzzy numbers, which could have different supports and shapes. For example, if the quantity x belongs to some interval, it's a probability, for example. You have some unknown probability between 0 and 1. It cannot be represented by a Gaussian because for a Gaussian, the support is a real line. Okay, or if you have a positive quantity, you want to have a half the positive real numbers. Okay, so actually we can have this by composing the random fuzzy set with a one-to-one mapping from the set theta to another space, lambda, and we get a new random fuzzy set. Okay, and I will define on lambda. Okay, this is a paper where this is a recent paper. So this is the idea. Okay, so you have this random fuzzy set x tilde, and you define a mapping psi, a one-to-one mapping psi from theta to some set lambda. So the first step, if you want to compose this with x tilde, you need to extend that mapping psi to fuzzy subset of theta. What is the image of a fuzzy subset of theta by psi? Okay, and in a theory of fuzzy sets, this is done by an operation called Zadim extension principle. Okay, so I will try to explain it in a few words because we don't have a lot of time. Okay, but just it can be done. Okay, you have a mapping from theta to lambda. You can extend it to compute the image of fuzzy set of theta. And this is done like this for any f tilde, a fuzzy subset of theta. You would define a new fuzzy set of lambda, which I denote like this, psi tilde of f tilde. It's a fuzzy set of lambda, which is the image of that fuzzy set of theta. And its membership version is defined like this. And the degree of membership of lambda to this fuzzy set is the supremum of f tilde of theta for all theta whose image is lambda. You take all the theta for any lambda, you take one lambda here, you take all the theta whose image is lambda, and you take the maximum the degree of membership, okay, in that set. Okay. But actually here this is very easy to but here we have a special case because psi is 1 to 1. So in that case, very easy. We just have this the degree of membership of lambda to the image of f tilde is f tilde of the inverse of psi minus 1 of lambda. So this, okay, maybe a little bit complicated for you if you're not familiar with the fuzzy sets, okay, but okay, it can be done. And we have this property that if x tilde is a random fuzzy set, then the composed mapping, if you compose x tilde with the extended function psi, which is psi tilde, then you still get a random fuzzy set. Okay. So now you get a random fuzzy set from omega to the power set of lambda. Fuzzy bounds. Okay. And you can easily compute the degree of belief and plausibility, okay, of events in lambda. And you can easily combine these two transform fuzzy sets because you have this property that the orthogonal sum of x1 tilde and x2 tilde composed with psi, it is just the orthogonal sum of x1 tilde and x2 tilde composed with psi. Okay. So if you know how to compute this, then you know how to compute this. So now we have some applications. For example, take psi being the exponential function and x tilde a Gaussian random fuzzy number. Then the composition of x tilde with the exponential here extended on the fuzzy sets, okay, on the real numbers, support 0 plus infinity. So it's a random fuzzy subset on the positive real line, and I call it a log normal random fuzzy number. Okay, we do the same here as in statistics when we define the log normal random, distribution. Okay, some y has a log normal distribution if the exponential has a normal distribution. So the same thing here. And so so here I show two examples of such log normal random fuzzy sets. So I represent them because it's not easy to represent. I show in red the contour function, in blue the lower upper CDF, and I show some random draws of the possibility distribution, and these are the lower and upper expectation, which I didn't speak about. We can compute the expression. So here there are two such things. So this defines, it's a model of of a belief function on the positive real numbers. If you have some unknown parameter which is positive, like a distance, for example, between 2 points is positive, you have a model to represent some evidence about this positive quantity by a belief function. Okay. And here you have the combination of these two. Okay, you can combine this information, these belief functions, and you just, because these are the images of some Gaussian random fuzzy numbers, we have seen that we can combine the Gaussian fuzzy numbers, so we combine them and then we apply the transformation to the result of the combination. Okay, here this is, I take the transformation is this logistic function, and now I have random fuzzy sets on the interval 0, 1. Okay. So for example, the unknown quantity may be a proportion or a probability. Okay. And I call such things logit normal random fuzzy numbers, and it extends the logit normal distribution. okay, that is used in statistics. And okay, you see here two examples again of these logit normal random fuzzy numbers and their combination. Okay, and you can not even another case is you take x tilde, that is a Gaussian random fuzzy vector, and you apply this transformation, which is known in machine learning as a softmax transformation. In statistics, I think we call it a logit transformation, something like that. And then the result is a logistic normal random fuzzy vector. And its support is a probability simplex. So here, for example, assume that I have, this is a space of probability distributions, okay, on the set of three elements. For example, you have in classification, you have three classes, okay, class 1, class 2, class 3, and the set of probabilities of this set can be defined by this simplex. And here I have contours of some fuzzy focal sets. Okay, and here this is a contour function of that. So you can define in an easy way that you can work with that a belief function on the probability simplex. Okay, for example, if you have unknown proportions of some components in the mixture, for example, or some unknown probability. So typically in Bayesian statistics, when we want to define the probability over probabilities, we use a Dirichlet distribution. Okay, so here it's something equivalent, but it's not a probability distribution; it's a belief function. So this can be used to define a belief function on a set of probabilities. And now you can also further extend this with mixtures, because you can define a mixture of Gaussian random fuzzy numbers as a Gaussian fuzzy number whose mode is a mixture, okay, of these Gaussian random vectors, and that also can be transformed by a one-to-one mapping. Okay, so for instance, here we have y1 tilde is a mixture of two logit normal random fuzzy numbers, and y2 is a different mixture. So we see here the contour functions in red, okay, and in blue we have the lower upper CDF, and we can combine them and we get the combination. So it means now we can define on any interval on the real line or on some regions of R to the P, we can define belief functions, okay, with any virtually arbitrary complexity because we take a mixture, okay. So we can, this contour, for example, can have any arbitrary shape. It's not restricted to unimodal or anything, okay? And we can combine them by this generalized Dempster's rule, which I call the product intersection rule. Okay, so now I will show, I think there are many applications of this. This is quite new, so if you, as this is new and you now know about it, if you want to do something new, you can maybe see how you can apply this. And I will show you one application to machine learning. Okay, evidential machine learning. Okay, you already have a good idea of it now because I told you about evidential clustering. Okay, and this is unsupervised learning. And Professor Zhongge Liu yesterday told you about classification. Okay, and okay, so this in general I call evidential machine learning an approach to machine learning in which uncertainty is quantified by belief functions. Okay, so until now there existed evidential clustering, you know about it, and evidential classification, you heard about it, but there was almost no work on evidential regression. Why? Because in regression, the response is a continuous variable, right? And we didn't know how to represent belief functions for continuous variables, okay? But now we know, so maybe we can now apply belief functions to regression. So here I introduce the notation. So we consider regression problem. So the response is denoted by y, so it's a continuous variable. For example, you want to forecast the temperature or the sales or anything. X is a vector of P features, attributes, And we have a learning set, okay, a set of n pairs of x and y observed for n individuals in the population. So I will describe a neural network model. I call it like this, ENN-REG, which quantifies uncertainty about the response for a given input vector x by a Gaussian random fuzzy number. I will denote it by y tilde of x. And this Gaussian random fuzzy number is associated with a belief function. I call it a predictive belief function. So this model is based on prototypes. Okay. So a long time ago, I published a paper on classification, a neural network for classification based on prototypes. This paper was published in 2000. Okay. The idea was that you have prototypes, and for each prototype, you consider each prototype gives you a piece of evidence. So you have a new x, you compute the distance to prototypes. Okay, so this is your feature space, x1, x2. You have some prototypes with some class. For example, this is the class 1, class 2, class 3, and so on. And now you have a new x. You look at the distance to the prototypes, okay? And then each prototype gives you a mass function that you combine by Dempster's rule. Okay? This is a little bit the same idea that the evidential KNN rule that Professor Liu recalled yesterday. He said that now we don't consider the nearest neighbors in all the training vectors, only the distances to prototypes. Okay? And in the neural network, the prototypes are learned, okay, are just parameters of the neural network they learned. So here we want to do the same thing, okay, with prototypes. And each prototype will give you a Gaussian random fuzzy number that you will combine. Okay. So the model is this. So I denote the K, we assume that there are K prototypes, denoted by W1 to WK. So first step, we compute the similarity between an input vector x and prototype K by this equation. Okay, we could take another kernel function here, but it works well with the exponential. So we see exponential of minus gamma k. Gamma k is a scale parameter, and this is a squared Euclidean distance between x and WK. So here, assume that you have here this WK, this is x. You take this distance, okay, you square it, and you apply an exponential, okay? And then we represent the evidence from prototype K by a Gaussian random fuzzy number. And because we have seen that it's suitable for describing some evidence on the real variable, the continuous variable. So here the mean is defined like this, okay? So it's a linear function of x. Okay? The idea is that locally around WK, you represent the regression function, you approximate the regression function by a linear function. Okay. So when x is close to WK, you assume that this gives you an approximation of the expected value of y given x, locally around WK. So this is a mean. Then you have a variance sigma k squared, which depends also on a prototype. It represents the conditional variance of y in the neighborhood of WK. Okay. Now I draw another picture here. Okay, so you have some data here. I take x as only one dimension. Okay, so here that might be some prototype WK. Okay, so you see that locally in the neighborhood, if x is close to WK, you can approximate the expected value of y given x by a linear function. Okay, and you see that you have some variability here around this value, okay, which is captured by sigma k. Okay, and this line is beta k transpose x plus beta k 0. So these are the mean and the variance. And then the precision is HK, this is a parameter that depends on the prototype, times the degree of similarity. It means if you are close, if X is close to omega K, okay, this evidence is strong because, okay, the prototype K gives you some good information about the value of Y for that X, okay, because X is close to omega K. If X is far from omega K, that information is less value, okay, so it should be taken more carefully, okay. So here the precision is the product of that similarity SK of X and HK. So then now we have those Gaussian random fuzzy numbers for each of the K prototypes, and we combine them. So actually here I take the product intersection, but I don't do the normalization that I explained before, okay? This is to simplify the calculations, okay? This is simplification, and actually it works, okay? So I use this symbol to indicate a different combination. We don't do that normalization. And we don't have conflict because we intersect Gaussian, so it's never zero. Okay, the support is a whole real line. And so now, okay, we can compute the parameters for this thing. So mu of X is some weighted sum of the mu K of X. Okay, the sigma squared is also some combination of a sigma K squared, and H of X is a sum. The precision is the sum of the precisions of each of these random fuzzy numbers. Okay, the calculations can be done in a neural network model, okay, where you have an input layer, okay, which are the inputs. Then you have two hidden layers. In the first hidden layer, if you have K prototypes, you have 2 times K neurons. Each pair here of neuron corresponds to one prototype. Here, one neuron computes the similarity SK of X between X and the prototypes, and it's a radial basis function neuron. The other neuron is a linear neuron, and it computes that linear approximation around the prototype. Okay? So you have K pairs of neurons. In the next hidden unit, the second hidden unit, you also have K pairs of neuron, where here one neuron just computes the square of SK of X, and the other one multiplies SK of X with mu K of X. Okay? So this is a squaring unit, and this is a product unit. Okay, and then you have the output layer with 3 neurons, one for the mean, one for the variance, and one for the precision, and they have connections. There are connections between this output layer and the second hidden layer, and also cross-cut connections also to the first hidden layer. So this view, okay, you could present a model without having this view, but I think it gives a good picture of the calculations, and it's helpful also if you want to compute the gradient, for example, of the error and so on. Okay. So how do we train such a model? So in the case where the prediction is given in the form of a probability distribution, for example, we call it a probabilistic forecast, okay, or prediction. You predict for say given X, your prediction is a probability density function F tilde. We typically measure the prediction error or loss by the negative log likelihood. This is called the negative log likelihood loss. That is minus the log of F tilde of Y. So if you have this is Y, you give your prediction in the form of a PDF. This is your the prediction of Y. You give it as a probability density function. And now y is here, the true, you observe the true y, what is, how much to measure the error? Okay, so the idea is you take here this value, okay, which is f of y, this f, sorry, this is f hat, this is f hat of y, and you take minus log of this. Take minus sign because this is a loss, you want to minimize, but you want actually to maximize here f tilde of y. Okay, what is the meaning of this? Okay, actually, we never observe a real number y. Okay, because when we have some observation, there is also some precision. Some of you are engineers, you know that when you have a sensor, we have some precision. Okay, so the result of the measurement is never a real number. So you can say that it's actually, you actually observe a small interval around y. Okay, so this is y minus epsilon, y plus epsilon. Okay, I call this like this. And this is an interval of plus or minus epsilon around y. Okay, so the probability of that interval, okay, is in this area, and if epsilon is small, it is approximately 2 times f tilde of y. Two times f tilde of y multiplied by epsilon. It's 2 times f tilde of y multiplied by epsilon. Okay, the proof is here. So the loss function L of y and f tilde is approximately minus the log of the probability of that interval plus some constant. Okay, so we want to maximize actually the plausibility of that, the probability of that interval. Probability of that interval. That is why we take the likelihood is an approximation. Okay. So now for us, the prediction is not given in the form of a PDF, but a belief function. How can we extend this? Here we don't have a probability, but we have a belief function and the plausibility function. Okay, so the first idea would be to replace the probability by the degree of belief. Actually, it doesn't work because the best forecast is always a probability. For any belief function forecast, there is always a better probability forecast. Okay, because you want to be as specific, and for the degree of belief to be high, you want the focal sets to be as small as possible. Okay, and so it's better when the focal sets are just points. Okay. So this doesn't work. If you take the plausibility, it also doesn't work because the optimal solution is always a vacuous belief function. And because for the vacuous belief function, the plausibility of the interval is always 1, so the loss is always 0. So in that case, you get a solution which is too imprecise. So in one case, you get a solution which is too precise. In the other case, you get a solution which is too imprecise. So the idea can be to take a weighted sum of both. So here we have the hyperparameter lambda, and the smaller values of lambda will give you more corpus prediction. So you may either fix lambda or try to determine it in some way. So now we can train the network to minimize the average loss. The average loss defined like this, but we know that in machine learning, we typically have a model with a large number of parameters. So to get a good generalization performance, we need to regularize. Okay, and here we have 2 regularization terms. Okay, here the first term, you see it's basically the sum of the precisions. Okay. So you want to minimize that. So you want to have the imprecisions, the precision as small as possible. So this has the effect of reducing the number of prototypes used. Yeah, because why? Because if you set HK to 0, is the precision corresponding to the prototype K, it amounts to discarding prototype K. Okay, so if you set some HK to 0, it's like you remove some prototypes. So you can see this term as favoring solution with small number of prototypes. And the other term is analyzes here the gamma k. The gamma k is a scale parameter in the exponential, okay? And actually, it can be seen as shrinking the solution towards a linear model. Because if gamma k is 0 for all k, you have a linear model. Okay, because locally, you have a linear model, and you take it, the neighborhood increases. So this shrinks, this second term shrinks the model to a linear model. So how many hyperparameters now do we have? We have epsilon and lambda and epsilon in the definition of the loss function. And here we have two, you need two coefficients, okay? 4 hyperparameters, it's a little too much. Because if you do a grid search, for example, it will be very expensive. Actually, here I have some heuristics. I set lambda to 0.9 and epsilon to 0.01 times the variance of y. It's like in the support vector regression, for example, for those who know this, there is also some epsilon in the error, and typically it is also fixed. Typically it's not optimized. Okay, and okay, I try to finish fast. Okay, now we need some notion maybe of calibration. The idea in probability, when you give a probabilistic forecast, you want to have the property that if the predicted probability of some interval is, for example, 90%, you want to have that in 90% of cases that, if you give an interval that you claim contains the true value of the response with a probability 90%, you want this to be true about 90% of the time. So now, here I define an interval, I call it an alpha level belief prediction interval, as an interval centered on the predicted mean, mu of x, such that the degree of belief of the interval is alpha. Okay, so an alpha level belief prediction interval is an interval centered on the mean, okay, whose degree of belief computed by our predicted belief function, is alpha. I say that the predictions are calibrated if for any alpha, these alpha level BBIs have a coverage probability at least alpha. That is to say, for whatever alpha, the probability that y is contains that interval is at least alpha. So when I compute, I have a method to compute these alpha level belief intervals. The proportion of time that this interval will contain the true y is at least, that must be at least alpha. So this property gives us some notion of consciousness, actually. And as in the probabilistic case, this property can be checked graphically by calibration plot. Okay, so here this is a small example. So here we have this model. So x has a uniform distribution between -2 and 2, and y is given by this equation. So it's the regression function is nonlinear, and the error also depends on x. So you have in blue, you have the true regression function. In red, you have the mu of x. So there's a predicted expectation. So here I use a learning set of 300 data, a validation set of the same size. I use 30 prototypes. So as you see, it's a lot. It doesn't matter because we regularize. Okay. Psi, the two hyperparameters for regularization, the two regularization coefficients were determined by minimizing the validation mean squared error. And here you see these three areas are three belief prediction intervals. Okay. In dark gray, you have the level is 0.5. In the next one is 0.9, and the largest one is 0.99. And you can verify, okay, the calibration property means that this band, for example, if you take the 0.5 band here, it should contain at least 50% of the data. And it is the case, actually. If you take this, the largest band, the 99%, actually it contains all of the data. So more than 99%. Okay, here this is the coverage rate. This is a proportion of these intervals that contain the data as a function of alpha. So the calibration property means that you must be above the diagonal. The coverage rate should be larger than alpha. Okay? So in blue, you have the intervals I compute with a probability plus or minus the mu of x plus or minus 2 times or some sigma of x. Okay, I don't take the h term into account. In red, I take the precision into account. It's a little bit more conservative, but it can be made more precise by multiplying the precisions by some number. This is some post-processing that we can do, and some experiments. So I will show them only quickly. So the message is that it works very well. Okay, it works as well or better than the best methods available so far. So these are some data sets which are frequently used to assess the performance of regression methods. So here I compute the root mean squared error. So just the accuracy here I don't take into account. I only use the mu of x, and because it should. Okay, it's good that it quantifies uncertainty well, but it should also predict well. Okay, so here the root mean squared error with some standard errors. And so this is the model I just described. This is a radial basis function network with its relevance vector machine, support vector machine, Gaussian process regression, random forest, and a multi-layer perceptron. And so the best result is shown is bold, and the results that are not significantly different from the best results are shown in bold. So you see, this is almost always either the best. It gives almost the best result or a result equivalent to the best result. Okay. So here I compare it to some other more recent deep learning models. Okay, this is probabilistic backpropagation, Monte Carlo dropout, deep ensemble, and deep evidential regression. So here this is a root mean square gain. Okay, and I take only a subset because I didn't run again all these methods. I use the results in the papers. So here you see again that it works as well on these data sets. And here they try to measure the calibration by what they call the non-negative likelihood. Non-negative log likelihood. Okay, and this is a common measure of calibration that is used in the machine learning literature. And you see, so here I use only the probabilistic intervals. Okay, I didn't take the precision. Okay, and even in terms of probabilistic calibration, it performs quite well also as compared to these state-of-the-art methods, which are based essentially on Bayesian reasoning. So even on this ground of probabilistic calibration, it works quite well. And here we show the calibration plots for some data sets. So here you have the blue is the probabilistic intervals. Okay, so in that case, it's almost calibrated. In red, we take into account the H, the precision. So it's more conservative, but maybe a little bit more conservative. So what we can do is use a validation set and change the precision values to be a little bit more precise. And we get that yellow, which is still calibrated, is still above the diagonal, but we're a little bit more precise. So here the probabilistic intervals are not calibrated. You see, they are overconfident. The model gives you more conservative results, and calibrated, but maybe a little bit too conservative, so we make them a little more precise, and we get the yellow. So here, even our model is overconfident. So we have now to decrease the precision terms. We have to tune also using a validation set. We tuned those precision to be less precise, and we get that yellow curve. And here, okay, here already the probabilistic method is already precise. Okay, so that's it. So to summarize, so I have defined what I think is a very general framework. Yeah, I call it theory of epistemic random fuzzy sets. It extends both possibility theory and Dempster-Shafer theory, and it allows us to represent and reason with uncertain information, which is both uncertain, imprecise, and vague. Okay. And actually, fuzzy sets are not only useful for linguistic information like tall, small, or big, and so on. There's also a relationship between possibility and likelihood. It was something that was present in Professor Martin's talk yesterday. Okay, and actually you can see the relative likelihood as a possibility distribution. Okay, so possibility information is not only linguistic information. Statistic, I claim, and I could argue, but not now because time is up. I could argue that statistical evidence is also well represented by possibility distribution. Okay? And when you do prediction, you use statistical evidence, which is a possibility, plus some random element, you get a random fuzzy set. Okay, I have also defined practical models of random fuzzy numbers and vectors indexed by 3 parameters. Okay, and this makes it possible to define belief functions on continuous frames that can be easily manipulated, combined, and so on. And this, I think, overcomes the severe limitation of Dempster-Shafer theory. And I describe an application to regression. So the neural network I describe has output 3 numbers. So one is a point prediction. The second one is an estimate of the conditional variance, and this can be considered as measuring random uncertainty. Okay? And the precision term represents epistemic uncertainty. And as I said, so there are other applications. One application is knowledge elicitation. If you want to represent someone's knowledge about a parameter, right, a continuous parameter, you can ask some questions and try to fit this kind of model. Even the transform Gaussian fuzzy number, okay? And that gives you a belief function. Okay, and statistical inference is also an important application, and I touched on it in this paper. Okay, so these are the papers. So this is describe random fuzzy sets, but on finite frames. Okay, so in a finite frame, a random fuzzy set is basically a mass function with fuzzy focal sets. Okay? So in this paper, I explain what a mass function with fuzzy focal sets. This is the paper with the general theory, and here I introduce the Gaussian random fuzzy numbers. Here, these are the transform for random fuzzy numbers and the mixtures. So we can have any shape. This is a paper on the application to regression. And this is the R package that contains that FREG model, okay, this the ENN-REG model, okay, that when you apply, you can use this package to implement this neural network model for regression. And all these papers are here on my personal homepage. Okay.